Okay, let's go ahead and get started. Quick announcements before we get going. First of all, so everyone's aware that the midterm's coming up next week. Those of you who have contacted us about midterm conflicts, we'll be sending you details with how that's going to be fixed soon, but so far everyone who's gotten in touch with us, we are going to be able to accommodate with an appropriate time. So wait for that. If you have not yet contacted us and you have a midterm conflict with another class or with something else, tell us now, because we're going to be making the final arrangements tonight, and after that it's not going to be possible to do anything. So that's it for midterms, other than also there is now a practice midterm posted online. That's going to work the same way as it did for the first midterm, so fill it out and then send it back in on Gradescope just saying that you've done it, and you'll get a little extra point. Any admin questions before we start the class? Okay, cool. So what we are talking about today on this slide are hidden Markov models. So if you remember, what we were doing last class was we were looking at Markov chains. And Markov chains are a special class of graphical model in which you just have, sort of every node has one child and you have a chain of these things. It's just a sequence. And we saw that these Markov chains have a couple of interesting properties. They admit an efficient inference algorithm, which is just doing variable elimination, but doing variable elimination in the right order. And we saw that they have some interesting conditional independence properties. That in particular, if I observe what's going on in the world at some time t, then an observation at time t makes the past from t independent of the future from t. So once I know what happened at time t, I don't care about anything that happened before it, because sort of everything that I care about history is contained in that one observation. And so we saw toward the end of the class that this means that Markov chains are actually not all that useful for modeling real-world phenomena or processes, where the issue is not that we kind of stumble around blindly and then occasionally get perfect information about the state of the world. But instead what happens is that we're constantly getting kind of noisy observations, and we never get to see, in some sense, the truth underlying reality. We only get noisy observations of the truth. And so that's going to motivate the model that we're talking about today, which is a hidden Markov model. So a hidden Markov model is just a Markov chain like we were looking at last class, where you have this kind of backbone of states of the world. But rather than observing those states directly, we're only going to be able to observe them indirectly by seeing noisy evidence variables that we've drawn here with the letter E and filled in gray. So this is what a hidden Markov model is in a nutshell, and this is the model that we're going to be looking at for the rest of class today. And we're going to see that like Markov models, these things have a special efficient inference ordering. They have some interesting conditional independence properties, but we're also going to see that they turn out to be useful for a much larger range of real-world problems. So to start this off with a demo, let's come back to this Ghostbuster thing that we've been doing over and over again. And I think I want this one. Come on. Okay, so this is hopefully starting to look really familiar. And you'll remember what we did last class with Ghostbusters, is we got a bunch of observations at the beginning until we were pretty confident that we knew exactly where the ghost was. So this somehow corresponds to knowing what our prior distribution over the states of a Markov model is, a Markov chain. And then we took this confidence about the initial state, and we just let time elapse over and over again without making any additional observations. And we saw that as time goes by, we can kind of slowly track some distribution of our belief about where the ghost is located in the world. But basically that distribution for most kind of natural transition functions here is going to decay over time. And if I keep stepping time over and over and over again, probably what's going to happen is I'm going to wind up with something that looks like a uniform distribution over states. And certainly what's going to happen is that my belief about the ghost position at time t is going to become less and less correlated with whatever information I had at the initial time step as time goes by. So this is a Markov chain. And what we're going to be looking at today is a slightly different version of this problem, where I'm going to get to maybe make one observation, and then time is going to elapse. And then I'm going to get to make another observation, and time is elapse. And then I'll make another observation, and time's going to elapse. And you can see here that even though that we're making a relatively small number of observations compared to, say, what we had to do to become certain about the ghost's location at the beginning of time, by making one observation per time step, choosing that observation wisely, and then letting time elapse, I can basically keep track of where the ghost is with perfect certainty, more or less forever. And so this is, like we were looking at before, what we're going to call a hidden Markov model instead. And what we're going to be looking at today are algorithms for tracking. I guess I've now lost the ghost. Reasonably confident about where it is. Are we feeling lucky? Which square? Top or bottom? Top. Okay. Good job. That was, the sort of wrong Bayesian thing to do, right? We were assigning slightly less probability to the top than the bottom, so we should have guessed the bottom, but top was right. Okay, so this is a hidden Markov model, the kind of inference that we've just done here, and what we're going to be looking at today is sort of solving the general problem of doing this kind of inference. So that's a Ghostbusters demo. Straw poll, did people find useful or at least entertaining our live demo yesterday with the blind person walking? Hands for yes. Hands for no, and be honest. Okay, people like that. So we can do another live demo today for HMM inference rather than regular Markov model inference, for which I will need 2 more live volunteers. Okay, live volunteer number 1 and live volunteer number 2. Excellent. Round of applause for the live volunteers. Okay, so this also involves a blindfold. I brought a handkerchief today to use as the blindfold, but then I used the handkerchief to blow my nose. So we are not going to use that. And I'm instead going to trust you to close your eyes at the appropriate time. So, what are your names, first of all? Ben and Zach. Okay, so Ben, stand behind the desk here. And Zach, stand in front of the desk here. This also involves participation from the whole audience. So what's going to happen here is Zach is going to walk back and forth from about the podium to the end of the desk here. And every time he reaches one side or the other, you are all going to clap. So let's practice this with everyone's eyes open. Come on. Okay, very good. You get it. And notice that this clap is not a perfect signal of when he has reached one corner or the other, because kind of the clap is a little bit smeared out in time, and you certainly don't know whether he's on one side or the other side just from clapping. Okay, so you're going to close your eyes, and your job is all the time to point at where you think Zach is located. Okay?
So I haven't closed my eyes.
You have to close your eyes, and you know where he is now, so point at him. No. You're going to point. So you're going to do this as he's walking across, and you want your finger to track where he is located. And your information about this is mostly going to come from the sound of people clapping, because your eyes are closed. Get it? Okay, so you know where he is now. Begin walking. Okay, good. Thank you. That is the demo. So the point here, you'll notice that what Ben did, he was kind of going along slowly because he wasn't quite sure how fast that was moving. And when everyone clapped, he immediately moved his hand over here because knowing that we had reached the end of the table provided some information about the state of the world. And from that, he was able to sort of make more accurate predictions as he was walking back in the other direction. So this is the HMM inference problem. I don't get to see what the true state of the world is, but I have a kind of noisy signal about what's going on, and we're going to go from that noisy signal to some kind of belief about the true state of the world. So that's today's lecture. Very fast recap of probability, because this is all hopefully really familiar now. We define conditional probability in the following way. We take our joint and we divide it by y. We can run this in reverse, and that gives us what's called the product rule, where I multiply a conditional distribution by a marginal distribution, and I get a joint distribution. We can also sort of extend this to the chain rule, which allows us to decompose a big joint into a product of a bunch of marginal or of conditional distributions. And finally, we have notions of independence. So things are kind of unconditionally independent if a joint distribution factors in the following way, and things are conditionally independent, basically saying exactly the same statement, but with some variable to the right-hand side of our conditioning bar. And in this case, we say x is independent of y, given z, as drawn here. This all hopefully looks very familiar to you all by now, but it's going to be important to have swapped in for today's lecture. So, finally, hidden Markov models for real. Like we said at the beginning of class, the sort of key issue with Markov models, and the reason that we think of them as kind of more of models of mathematical processes than things that we use for artificial intelligence out in the real world, is that they're not good models of the agents that we actually build. Because the agents that we actually build are able to make observations all the time and the thing that is hidden from them always is the true state of the world. So we're now living in a world not where we're going to periodically make observations of the true state, but rather where we're constantly going to make noisy observations and never actually get to observe the true state. So to make this kind of concrete, we have here our favorite example, the weather. So let's say here in particular, you guys have graduated from Berkeley, you've got an offer from Facebook, so you've gone to work for Facebook. How many people here have been to the Facebook offices down in Menlo Park? A couple of hands. Okay, it's amazing. It's like Disneyland. There's this kind of big corridor down the middle, and there are restaurants off to either side, and there are people walking around in strange clothes. So Facebook is really nice. And so you take your job at Facebook, fresh out of college, and you go to your desk, and you find that Facebook, in fact, is so nice, you never want to leave. So there's food there, so you never have to leave for food. They do your dry cleaning there, so you never have to leave to do the laundry. There are little nap pods, so you never have to leave to sleep. So you're just at your desk all the time, and you have no connection to the outside world. You still care a little bit what's happening in the outside world, outside, I guess, your windowless office. And in particular, maybe you want to know what the weather is just to feel like you have still some connection to the rest of the human species. So you observe that your coworkers, who do sometimes enter and leave the premises, sometimes carry umbrellas with them, and sometimes don't carry umbrellas with them. So you're never actually going to get to see what's happening outside, but you still want to be able to figure out what the weather is outside, and the only information that you're going to have to determine this is whether or not your coworkers are carrying umbrellas. So we can specify this all with a Bayes net like we have up on the screen here, and hopefully by now you know kind of what probability distributions we're going to need to specify this Bayes net, right? The first thing that we're going to need is some kind of initial distribution such that when you start making your observations, the first day you walk into that building knowing that you're never going to walk out again, what's the probability of the weather being one thing or another? We're going to need, like we had in the Markov models that we were looking at last class, some kind of transition distribution that's going to tell me, even if I weren't making any observations at all, how does my knowledge about the weather today affect what my knowledge about the weather tomorrow should be? And so far, with just those two pieces defined, what we have is a sort of ordinary Markov model of the kind that we were looking at last class. What we're additionally going to add to that to get to a hidden Markov model is an evidence distribution. So I'm going to have some distribution that tells me, given what the weather is today, what is the probability that I see one of my coworkers bringing an umbrella with them or not? And so we can write out these two probability tables, and these kind of, for this example that we've set up here, have the intuitive behavior that you would expect, right? Maybe my initial distribution over times, this P of x1 here is uniform because I don't want to encode any biases into the process. The transition distribution, which is this table on the left, is going to say if it's raining today, it's probably going to keep raining tomorrow. If it's sunny today, it's probably going to keep staying sunny tomorrow. And otherwise, we'll switch states with some smaller probability. And then finally, we have this observation distribution, which says if it's raining today, it's very likely that I see my coworker bringing the umbrella with them. If it's not raining today, it's pretty likely that my coworker has not brought an umbrella with them, has left the umbrella behind. But then the opposites of those two cases can also happen with some small probability. So are people happy with the sort of general setup we have here? What problem we're trying to solve and what information we need to solve it? Okay, good. And so the key thing to notice here is that, like we had with ordinary Markov models, we only have 3 probability tables defining this kind of infinitely large graphical model that extends over all time. And that's because all of the transitions are the same and all of the emission distributions are the same. So we're assuming that basically the kind of dynamics of the world don't change over time. So this is the case for the weather. We can sort of do a similar example of this for Ghostbusters land. And so like we said, it's often kind of reasonable to start with a uniform distribution because you hope kind of that everything that comes in is going to come from the evidence rather than your biases about the problem. We're going to specify for the Ghostbusters problem some kind of transition distribution that says, like we were looking at on the kind of live example there, the ghost is probably going to move around the board in a clockwise way, but sometimes it'll move in a random direction, and sometimes it will stay put instead. And so to kind of draw this concretely, what I want is that if I know I'm at the top square of the board, I'm going to have some distribution that tells me probably I move to the right, maybe I move to the bottom, maybe I move to the left instead. So again, so far what we've defined is an ordinary Markov model, and I can kind of start this from some initial distribution and run it forever. But in a hidden Markov model, we are additionally going to have some kind of distribution over evidence. And especially in robotic settings, you'll occasionally see these things referred to as sensor models, because that's basically what they are, right? These evidence variables, these E's, or what we have on this slide is R's, correspond to sensor readings that you're going to get from the world that are some kind of noisy reflection of the underlying reality. And so we saw in the Ghostbusters example that the sensor either shows up as green when the ghost is close, or as red when the ghost is far away, and so on. So just another example for making it concrete. So what can we say about the joint distribution of a hidden Markov model? Again, this is something you guys should be really good at right now, right? This is just a Bayes net. It's a Bayes net with a particular structure, but it's just a Bayes net. And so if I want to write down the joint distribution over a full sequence of hidden states that might have occurred in the world, and over all of the evidence that we might have seen, that's just going to be a joint probability that looks like what we have down here at the bottom of the screen. Does anyone not see how we got from the structure of this Bayes net to the particular joint distribution that we've written down at the bottom? Okay, good. So like we always like to do with Bayes nets, let's talk a little bit about some of the conditional independence assumptions that are implied by the Bayes net here. So we've written a couple of them up on the screen, right? If I observe this evidence variable x1, the very first one in the chain, then my evidence at the first time step becomes conditionally independent of everything else that might happen forever, right? It becomes conditionally independent both of all of the future hidden states and of all of the future observations. And this is basically the analog to what we saw in Markov models before, where if I observe any of these hidden states, the future becomes conditionally independent of the past. There are other conditional independence assumptions that are implied by a model like this, and I think, well, yeah. So you guys tell me, what's one other conditional independence assumption that is implied by the particular Bayes net structure we have here? Yeah, sure.
If you observe, like, let's say, x2, then x1 and e1 don't matter.
Okay, x1 and e1 don't matter. What are x1 and e1 independent of? Are x1 and e1 themselves conditionally independent if I observe x2?
I guess they're independent of x3.
They're independent of x3, right? This is kind of the same question, that whenever I observe one of the variables along this backbone here, everything that comes before it becomes conditionally independent of everything that comes after it, but not necessarily, if we've kind of partitioned time into two pieces now, in the time before t, things still depend on each other, and in the time after t, things are still going to depend on each other. Okay, so what we saw in Markov model land was that we would make observations of the hidden state. What we're seeing in HMM land is that we're never going to make observations of the hidden state, and we're only ever going to get to make observations of the evidence. So think about, for the next 30 seconds, is there a set of observations of evidence that you can make that will cause any random variables in this graphical model to become conditionally independent of any other ones? So 30 seconds. Yeah.
So you're asking if we can create a graphical model where they are independent.
Well, so there's only one model, right? This is kind of the only model structure we care about ever now. And so the question is there some set, sorry, we don't have the iPad today, so I'll do this on the board. Is there some set of observations we can make of these evidence variables down at the bottom that will introduce, sort of cause additional conditional independences to appear in this network? Okay, so show of hands. Who thinks that there are things that will become conditionally independent given the bottom. Who thinks there are not things that will become conditionally independent given the bottom? And who's not sure? Okay, cool. So there are, in fact, no things that will become conditionally independent given observations of the bottom. And the easiest way to see that is to remember our deseparation rules, right? So every path through this BaseNet is basically going to look, let's do this in another color, is going to look something like this. Right, so either I can start from on the backbone or I can start with one of the evidence variables. I can travel some distance along the backbone and then I can either stay there or I can come down to one of these evidence variables. If I look at every triple along one of these paths, it's either going to be what we call the causal chain before, when we're moving in this direction, or it's going to be a common cause, which is like these three nodes here. So everything is either a causal chain or a common cause. And we know that those are both examples in our little deseparation algorithm where the links are active unless we observe the thing in the middle. So the question is there any triple here where the thing in the middle is one of my observation variables rather than one of my backbone variables? And the answer is no, right? Because these things have no children, the way we have this model, and there are no V structures, we can never wind up with these nodes in the middle of any of these triples. So there's always going to be an active path that travels along the backbone in our HMM. And that means that no observations of evidence will in general allow us to kind of forget history. So this is a really important fact about hidden Markov models, that all of the evidence that you have ever observed over all time matters. And that you're just going to keep accumulating evidence as you continue to make observations, but you were never, on the basis of that evidence, unless maybe your probability tables have a certain very special structure, going to be able to forget anything that ever happened in the past. Is it clear to people what we did here and why that matters? Okay, cool. So before we go on to making this a little bit more formal, I want to start by talking about some real-world examples of where these things come up. I mentioned a couple of these in yesterday's lecture on Markov models, and it turns out those were all lies because we don't use Markov models for anything. We use hidden Markov models for everything. So when we do speech recognition, I guess it says on here already, but the observations that you get at the bottom are acoustic signals, are waveforms, are whatever sequence of vibrations is coming into your microphone. And what we're trying to infer, the kind of hidden signal that produced those waveforms, is the actual language that's being spoken, right? So all we ever get to observe in a speech transcription model is waveforms, and what we want to recover is a sequence of hidden states corresponding to the sounds or the letters or the words that were actually being spoken into the microphone. So this is a kind of canonical example of a problem that we solve using hidden Markov models. Another thing, this is probably less true than it was when we gave the class last year, but still classically the way a machine translation system, so something that's going to take in Chinese sentences input and produce an English sentences output, or a French sentences input and an Arabic sentences output, work like hidden Markov models. And they're a kind of funny hidden Markov model where the observations, the evidence variables that you see down at the bottom are words of the foreign language, or phrases of the foreign language or whatever, and the hidden states are words or phrases of the language that you're trying to translate into. So you imagine a kind of noisy process that says, well, the way language works is I start with a sequence of English words, and I'm going to kind of damage those English words somehow in a way that turns them into French. And so if I see then a French sentence, what I want to recover is the kind of true English sentence that produced this French sentence. And, this is obviously not the way language works for real, but it turns out to be a surprisingly effective model for doing statistical machine translation with. So machine translation is another HMM case. And then one of the canonical examples that we're going to see over and over again in this class, and one of the things that was used to motivate the original development of a lot of these techniques that we're talking about today, is robotics, right? So a robot lives in a world where it doesn't know really where it is. It doesn't, get access to some bird's eye map that shows exactly where it's located. It has some number of sensors. Those sensors are in general not great, and maybe they're unreliable, or maybe they're picking up things that aren't there. And also the transition model of the world that the robot has access to. Kind of the robot's model of what's going to happen if it takes certain actions or if it stands still and lets the world elapse is not going to be perfect, because that, sort of doing that perfectly requires simulating all of physics perfectly, which is just not something that we know how to do or that would be computationally tractable in any case. So our robot's equipped with some kind of approximate model of how the world works, and it's equipped with some approximate model of the relationship between its sensors and reality, and it has to be able to synthesize those two things in order to get a really precise notion of where it is physically located. As a kind of historical accident more than anything else, the problem of doing inference in hidden Markov models is something that lots of different people from lots of different fields at different times have kind of independently invented. So you'll occasionally see it referred to with a bunch of different names. So robotics people will typically call this a filtering problem, doing inference in an HMM. In, I think, signals communities, it's called a monitoring problem. In sort of more like discrete settings or natural language processing, computational biology, you'll just hear this referred to as the forward problem. And there is a backward problem also, but we're not going to talk about it in this class. So all of these mean the same thing, right? When we say filtering, when we say monitoring, when we say solving the forward problem, we just mean, given a bunch of evidence up to time t, how do I figure out what the state of the world is that's generating that evidence, also at time t? And so we're going to be modeling all of this, and we're going to see a sort of formal definition of this 10 or 15 minutes from now in terms of belief. So this quantity that we've drawn on the slide as b of x, we're going to use throughout this class to refer to our belief about the state of the world at some time t. Yeah, that's it. So the last bullet point here, there's a special case of HMM inference where you don't have discrete spaces like we look at in this class, but you actually have continuous state spaces, kind of XY positions or angles or whatever. For this version of the problem, the HMM inference algorithm is called a Kalman filter. The Kalman filter was originally developed for space travel, where you have actually a very similar problem to the robot motion problem, right? Where my sensors are crappy because it's 1960, and my model of physics is terrible because, n-body problems are hard, and I don't really know how gravity works. But I still somehow have to get people to the moon. And if I'm off by even a little bit, then all of those people are going to go way out into space and they're never going to come back. And this is a problem that you can solve using inference in HMM. So what we're learning today is how to get to the moon in 1960. Here's a slightly easier problem than getting to the moon. This is this robot localization problem. We're going to look at this in a kind of more concrete setting. So what we have drawn on the slide here in red is some kind of toy robot. And the robot has 4 sensors. Well, 2 like this, 2 like this, and those sensors are only going to be able to tell the robot whether it sees a wall in the direction that the sensor is pointing or not. And in particular, they're not good sensors, and so it's possible that one of those 4 sensors at any time step will have also made a mistake. So this is kind of the only observation that the robot is able to make of the world is where the walls are. The robot also has some model of the dynamics of the world. So, as it's set up here, it's just going to try to drive, I guess, to the right, as we've drawn it on the screen right now. The robot's going to try to drive to the right. It's going to keep sort of doing its move right action at every time step, but that might not always succeed. Maybe the gears get stuck or the motor's got something wrong with it or something. And so with some small probability, the moving right action that the robot tries to take will fail. And the problem that we're trying to figure out here is basically to figure out where the robot is located as time goes by. Does this remind you of any homework problems that you've done in this class? The ladybug problem, exactly. So, you remember we had a thing before that we talked about as a search problem, where I had a grid that looked like this, and there was some bug. And what we said was, the bug is located somewhere on this grid. I don't know where. And I want you to choose a sequence of actions that will cause this bug to reach a particular square that you're certain about. And the solution that hopefully you all came up with is that you say, okay, the state that I care about here basically corresponds to a Boolean variable for every cell in the world that's going to be true if I think the bug might be in that cell, and that's going to be false if I think the bug is not going to be in that cell. And then you knew that different actions that you could take in this ladybug world would allow you to cross off cells from the list of the cells that the ladybug might be located in. Do you all remember this homework problem? Okay, cool. you have already invented inference in hidden Markov models, because that's exactly what you're doing when we say that this is a search problem, is you start with some belief about where the ladybug is located, and over time, your knowledge of the dynamics underlying the world, the transition model, allow you to become more and more certain in your belief about where the ladybug is. So all we're doing today when we talk about HMM inference is solving basically the same kind of problem, but now in a probabilistic setting where sometimes your actions fail with some probability, and rather than kind of knowing exactly where things are. I guess in the ladybug problem, you never got any observations of the world. Here, we're also going to be able to get some noisy observations of the world. So let's look at what happens when we actually play through this model in the robotics setting. So the robot's going to start out in this position, up on the top left here, but remember that the robot doesn't know that. And so what we've drawn in gray in the background corresponds to the robot's own belief about where it might be located. And at the beginning of time, before the robot has tried to move, and before the robot has made any observations, we're just going to assume that the robot's belief corresponds to a uniform distribution over all of the places in the world. Okay, so like we said before, the next thing that's going to happen is that the robot is going to make an observation of the world. And immediately, we've changed our belief distribution about where we're located, right? We have become sort of pretty confident in some set of cells that we've shown in dark gray. We've become slightly less confident in some other set of cells that we've shown in light gray. And we've become totally certain that we are not located in any of these cells that are shown in white. Why is it that, for example, I know I'm not located in one of these middle cells on the left side of the board? Yeah?
Because you wouldn't see a wall.
Okay, yeah, so we know that these sensors might make mistakes, but they're not going to make that many mistakes. So what would it take for you to be sitting on the left side of the board and actually make the observation that we made here, that there's a wall above and below me? Well, the top one would have to be wrong, the bottom one would have to be wrong. Those would both have to say that there are walls when in fact there are no walls, and the left and the right would have to be wrong because those have to say that there are not walls when in fact there are walls. That's 4 mistakes, and the assumption that we have, our observation distribution here, tells us that the sensor will make at most 1 mistake. So that's why we've been able to totally rule out these kind of vertical corridors, and then we have a couple things shown in lighter gray, and those correspond to places where the sensor might have made 1 mistake. Okay, so we've observed the world. If I just sit here, am I going to be able to become any more confident in my location in the world? Who thinks no? Who thinks yes? Okay, so what would I do if I sit here? If I stay at this current position, how is it that I will become more confident? Exactly. Okay, so the other assumption that we've made here, right, is that all of these observation distributions are the same at every time step. And that means if I stay put, if I stay parked right here, the fact that I made a mistake with my sensors at the previous time step has no bearing at all on whether I'm going to make a mistake at the current time step. So for these cells that are shown in light gray, I'm going to be able to rule those out more and more because those sort of assume that I made one of the mistakes with the sensors. And for them to continue to be plausible, I have to continue to get sensor readings that are consistent with those. And this is something that we don't expect to happen. Is that clear to people? Why I will continue to collect information even if I stay put. Okay, will I be able to become totally confident about where I'm located on the board if I stay where I am? Who thinks yes? Everyone thinks no. Okay, good. And the reason for that, right, is that all the cells that we've shown here in dark gray are cells that are 100% consistent with my current observation. So even if I make this observation over and over and over again, and it really is the ground truth, that's not going to help me distinguish where I am among all of these cells. So what the robot's going to do instead is it's going to move to the right. And what happens after the robot moves to the right is we have something like this. Okay, so the cell where I used to be last time is still shown in gray. Why is it shown in gray? Someone on this side of the room. Yeah. Yeah, so the sort of state of affairs that would have left me behind is the state of affairs where I tried to move right and I failed. And in that case, I would still make the sensor reading that I'm getting now. So there is still some probability that I got left behind in that previous state. And all of these other gray states basically corresponding to starting places that we might have been at the last turn, moving right, and making the observation that we just moved. So you'll see it's kind of getting narrower from both directions. It's getting narrower from the left direction because sort of that's consistent with me actually successfully moving to the right, and it's getting narrower from the right direction because I'm able to rule things out on the basis of sensor observations, where I would have seen this corridor otherwise had I been right before. So we can just keep doing this over and over, and eventually we're going to wind up in a state that looks like this, where the robot is pretty sure it's on top or bottom at this horizontal position, but it has no information about the vertical position. What's going to happen when it moves to the right next? Yeah. Yeah, so it's going to become pretty sure that it's on the top because now I'm going to see that sort of in the corridor below me there is no wall, and so the only way for that to be consistent with everything that I'm observing is for that to be an error, and that's going to be unlikely but not impossible. So this is what robot localization looks like, and again, the key thing to take away here is that we're using a combination of our dynamics model of the world, of what happens when the robot tries to move to the right, and our emission model of the world, sort of what states of reality can give rise to particular sensor observations, and we know how to put those two things together in order to come up with a distribution about where the robot is located. One thing that I think is conceptually useful is to just play through this whole thing again from the robot's point of view, right? So remember the robot, we drew this red thing on the screen. The robot has no access to the red thing, and what it sees over time is just a distribution over cells that looks like this. And so this is really what's going on when you're doing HMM inference, is that you have some distribution over all of the possible states that you might be in, and kind of you're never certain about where you're located. All you ever have access to is this distribution, and anything that you want to do is going to be based on that distribution rather than on some true underlying state. Questions about the high-level pieces of this before we move on? Okay, so all we have left to do is formalize all of this and talk about this kind of in mathematical terms. How are we going to figure out how to solve this problem? This inference algorithm that we come up with here is going to look a lot like the inference algorithm that we came up with for ordinary Markov models, and it just has to incorporate one extra piece, which is what do we do with these evidence variables that we have down at the bottom. So before we launch into the full algorithm, I want to talk about kind of what the base cases are here. The first base case that we're going to be looking at is exactly the same one that we had for HMM inference yesterday, which is that I want to figure out what the marginal distribution is that I'm in some position at time t equals 2. And the way I'm going to figure out the marginal distribution over my position at time t equals 2 is using my distribution over the position at time t equals 1, right? So remember what we did last class is to get p of x2, we start by forming the joint distribution over x1 and x2. The structure of our BaseNet, the structure of this graphical model, tells us that that thing decomposes into a product of the marginal probability of being in a position at x1 and some conditional distribution of x2 given x1, and then we sum out, and that gives us the distribution at x2. And once again, the way we've drawn it on the screen right here, this is just variable elimination. It's variable elimination in a kind of particularly simple class of graphical models that only has two random variables. So hopefully this looks familiar from yesterday. The only other base case that we have to think about here is what to do with the evidence. And so what this looks like in a kind of isolated example is I want to figure out what the posterior distribution over my hidden state is, given that I've observed some evidence variable. The way we're going to do that is as follows. And this also hopefully looks kind of familiar from when we were talking about BaseNet inference in the general case, right? So I want to get from x1 I'm trying to get x1 given e1. What I have given to me in the BaseNet is e1 given x1, and so I just need to flip that around. And once again, the way I'm going to do that is I first form the joint probability distribution, and that's something that I know how to do from the structure of the BaseNet. And then I'm going to divide that out by the marginal probability of e1. And this thing that we've divided through here, this marginal probability of e1, is some kind of constant term that doesn't actually depend on x. So we could either compute it explicitly, which would be kind of a pain and require some work, or we can just say there's some constant. And I know that at the end of the day, I'm going to have to divide through by that constant in order to get a proper probability distribution over values of x1 at the end. And so that's what we're going to do here. And so this, again, little fishtail symbol that we've drawn means that the second line is proportional to the first line up to some constant that doesn't depend on x, which is the variable that we actually care about querying. So we form the joint distribution, which is what we want, up to a constant. We compute the joint distribution, and then if I wanted to figure out that posterior right now, I would just divide through over all of the values of x in order to turn it into a probability distribution. Does this look familiar? Okay. So all we need to do now is to figure out how to put these two things together and form from them a complete inference algorithm. Like we said before, it's going to be useful to define this inference algorithm in terms of a bunch of quantities that we're going to call B. And B stands for belief. So when I write B of xt, which we'll sometimes also write B sub t of x, that means my belief about where I am located in the world at some time t. And by this B of xt, all we mean is the probability, the margin, or the probability of being at xt, having summed out all of the x's in the past, given all of the evidence that I have observed up until time t. So this is just notational shorthand so that we don't have to keep writing down that we condition on all of the available evidence, which is going to be kind of a given. So what we want to model in this stage is the passage of time, is what happens before I make any observations and just allow time to elapse. So think of this, in the case that we were looking at before, as what are we doing, what is the robot doing when it moves to the left, but before it's actually looked at any of the sensor readings, or in this kind of walking back and forth thing that we were doing at the beginning of class, what has happened when we know that Zach has started moving, but before anyone has clapped their hands. And that's going to look like the following. And this is basically just a generalization of that base case that we looked at on the previous slide. So I want to get my belief at x sub t plus 1. I have all the evidence up to time t. And we're going to assume now that I've computed my belief up to time t. And that means I can write this down in the following way. I can, again, first form the kind of distribution over both x sub t plus 1 and x sub t at the same time, and then sub out x sub t to get x sub t plus 1. And I know I can write down this distribution over both of them, given all the evidence, as a product of two things. The probability of being in state x sub t plus 1, given that I'm in x sub t, and the probability of being in x sub t. And the second term, of course, we know from the structure of the Bayes-net, depends only on where I was at the previous time step and not any of the evidence that I observed before, right? So this is saying before, kind of as we were looking at before, if I actually know what's going on here, but I don't care about any of the evidence at the previous time steps. And so, this is not sort of a real quantity that we ever have access to, but we have something like it that comes up in this sum here that we use for computing what happens as time elapses. So this is that process, and if we want to write it down compactly in terms of other quantities that we know, we can call this thing B prime. And so, we're going to have B's and we're going to have B primes. B is your post-observation, your post-observation distribution over what's going on. B prime is your pre-observation distribution over what's going on. So, B of x sub t is where do I think I am at time t, having observed all of the evidence up to and including the evidence at time t. And B prime of x sub t plus 1 is my belief about where I am at x sub t plus 1 before I have observed the evidence at time t plus 1, observing only the evidence up to time t. And we can see here that we form B prime just by multiplying together the B from the previous time step and the transition probabilities and then summing them out. Once again, this is just variable elimination, right? And all we've done here is we've kind of written down a convenient shorthand because we know there's an efficient dynamic program for this particular class of graphical models. Yeah?
I'm still a bit confused as to how you have, why you're able to ignore everything previous to it if you're not observing the actual state.
Okay, so, again, I think the key thing here is to pay attention to what's a capital letter and what's a lowercase letter, which maybe seems like kind of silly advice. But the point is, what I am assuming is that I have access to the marginal distribution over where I might be at time t. Okay? When I'm trying to figure out what's going on at time t plus 1, I'm going to first construct kind of the distribution jointly over what's happening at time t and what's happening at time t plus 1, given all the evidence. And so what you're saying basically is, well, I don't know where I am at time t, but I might be in one of two, if these are binary random variables, I might be in one of two worlds. I might be in the sort of plus x world at this time, and I might be in the minus x world at this time. If I assume that I'm in either one of those worlds, then I know what has happened here, and I can forget about everything that's happened in the past. And so what I'm going to do is I'm going to sort of take those two worlds together, and I'm going to weight the probability of where I might be now according to the probability of each of those being the world that I'm in right now. So in particular, we haven't suddenly magically gotten access to the true state of the world at time t, but we can weight the two things that it might be by our belief about where it was. And in particular, like we were saying at the very beginning of class, this belief of where I am at time x sub t incorporates all of the evidence that I have observed up until time t. Yeah? Yeah. Yes. That's x sub t plus 1. Yeah, sorry. So other questions about what's going on here before we move on? Okay, cool. And so, sorry, if you kind of want to think about this in intuitive terms, what this update that takes me from a b sub t to a b prime sub t plus 1 is that I'm kind of taking my belief distribution and I'm pushing it through the transition distribution, and that's going to cause me to alter my beliefs in accordance to how my transition model tells me the world works. And, sort of general cautionary note, pay attention to subscripts because subscripts really matter, and pay attention to primes because it matters whether we've observed the evidence or not. So yeah, to make this kind of concrete, let's go back and look at examples from this Ghostbusters world. This thing that we did right here is exactly the same thing, once again, that we were doing in Markov models class yesterday. So, if I know where I am at some time t equals 1, and I run this forever, over time, if I don't get to make any more observations, probably that belief is going to become more and more diffuse. And this is what this time-elapse update typically looks like. So that deals with one of the base cases that we were looking at before. And the only other one we have to deal with is how do we actually incorporate observations of the world into our understanding of what's going on here. So remember, B prime we've just defined in the following way. This is my distribution over states at time t plus 1, given the evidence up to time t, but not including t plus 1. And what I want to get now is from this B prime at t plus 1 back to a B at t plus 1, which will incorporate all of the evidence that I have available to me. So we're going to do that in the following way. We write down the probability of being in some state at t plus 1, given the evidence up to that time, which remember is just our B at t plus 1, like we did in this base case that we were looking at before, but now also conditioning on the evidence. So this first line just falls out of the rules of probability, and we can once again play this trick of saying that the denominator here is some constant that depends on all the evidence that I've seen, but doesn't actually depend on any of these hidden values of these x variables. And so we're just going to throw it away, and we're going to remember that we have to normalize at the end. And so I do that, and now I have a distribution over my current state at this time and over the evidence at this time, and my Bayesnet tells me how to write that down in a way that sort of, if I know where I am at this time, once again, I don't actually care about anything that's come before. And we're playing the same trick basically of saying, okay, well, we'll think about the world where I might be in one state, think about the world where I might be in the other state, and weight the outcomes of those two worlds accordingly. And that's going to give us, finally, another update rule that looks like this. So on the previous slide, we saw how to get from a B at time t to a B prime at time t plus 1. And here's getting from a B prime at time t plus 1 back to a B at time t plus 1. And this is super easy. All we have to do is we take this, our current belief distribution under the transition model, and we reweight it according to the evidence that we've actually observed. This is going to give us something that's not a proper probability distribution, but that can be turned back into one just by normalizing. And again, you can go home and convince yourself that this constant that we've thrown away is something that's easy for us to compute and is the same as what you get by just dividing through here. So this looks like the example that we were doing, sort of the second example that we had of Ghostbusters Land Today, where I get to make observations of the world. And in general, the kind of intuition here is that the more observations I get to make, the more confident I'm going to become in my belief about where the ghost is located at a particular time. This is not universally true, but for kind of real sensor models, this is actually how things work. To tie this back to the weather example that we were looking at before, we have an HMM that looks like this, right? So you'll remember that I started off with some initial distribution over whether it was sunny outside or whether it was rainy outside on the first day that I walked into my Facebook office, and we said that that was maybe going to be a uniform distribution. Can people read the slide? Mostly? Okay, so in particular, the thing to notice here is my prior distribution over whether it's sunny or rainy is the kind of belief that we've been calling a B prime, a pre-observation belief, a pre-evidence belief, because it doesn't take into account anything that I've actually been able to observe. On the first day, I will start with my prior belief about what the weather is, and I'll observe that my coworker comes in, and maybe here I observe that they came in with an umbrella, and so that's going to cause me to reweight my belief about what the weather is right now, according to the probability of, sort of, if it was rainy, should I have seen this umbrella? If it was sunny, should I have seen this umbrella? And that's going to give me my true belief, my post-evidence belief at time t equals 1. And you'll notice in particular that we've become more confident that it's rainy having seen this umbrella. End of day 1, I fall asleep at my desk or my nap pod or whatever. I wake up the next morning, nobody's in the office yet. I can still form a belief about what the weather is today before anyone else has gotten into the office. And the way I'm going to do that is I'm going to take my belief from the previous night and I'm going to pass it through this transition distribution that says, if it used to be rainy, how likely is it to become sunny, and vice versa. And so that's what we have drawn here. And you'll notice that when I made this update to my belief, I became less confident, right? Because in general, these things get smeared around. The distribution we were looking at before said, if it was rainy today, there's a 0.7 chance that it's going to be rainy tomorrow. And so once we kind of push this belief that I had before through my transition dynamics, I've come up with a belief that still thinks it's probably rainy, but that is less confident than it was before. And that's consistent with a world in which we think the weather stays the same most of the time, but not always. Okay, so we've done that. Now my coworker walks in. I see that my coworker once again has their umbrella. That's belief that's mostly consistent with it being rainy outside, and so I reweight my B prime distribution again, and this is going to give me finally my belief after seeing an umbrella 2 days in a row. And you can see from the example, the example here, that we're even more confident than we were before that it is rainy today. Questions about this example? Okay, so, and what we're going to be able to do as we go through all of time is basically alternate back and forth between making these two kinds of updates that we've looked at here. And that alternation is what's going to ultimately allow us to derive a belief about the distribution at any fixed time. And once again, I think that, the thing that's really important to remember here is that this is just variable elimination. And it's variable elimination in the following order. I start with what's here. I sum it together with this. I join it with this, and then I sum it out. Like so. I take these two things, and I join them together, and then I sum this one out. And that's my time elapsed. I take these two things, I join them together, and then I sum this out. That's observing the evidence. I take these two things, I join them together, and I sum it out, and so on. And so when we write down this kind of mutual recursion for computing what this belief distribution is for any point arbitrarily far in the future, all that is me choosing an efficient variable elimination ordering on this particular Bayes net. And we know that there's always going to be that efficient variable elimination ordering because if you kind of squint at this thing, it's a tree, right? I can pick any one of these nodes, and because everything kind of only has one child here, I guess that's not true. Everything only has one parent, it's a tree. And trees always have efficient variable elimination. So this is what's going to allow us to finally come together into what's called the forward algorithm. Oh, yeah, sorry, question.
Sorry, which you just drew.
Yeah.
When you erase the evidence node, don't you, when you variable eliminate evidence node,
Yeah.
kind of like throwing it away.
So remember, when we're doing variable elimination, it's not just throwing things away. Kind of, my BaseNet tells me probability of this given this, probability of this given this, and so on. Yeah, sorry, I guess I've actually been, I did not draw that the way we've been doing this in class. So thank you, yeah. Because these are evidence nodes, I guess the way to think about this instead is that you're making updates that look like this, where slowly over time, I guess the arrow points the other direction, but slowly over time, as we knock these things out, you know, we will be keeping around, direction of the arrows doesn't really matter, but we're keeping around all the events. The key thing to remember is just that if I know the marginal distribution at this time, that tells me everything I need to know about the past. And so I can compute that marginal distribution for any time in the future based on all of the evidence that I have in the past. And once I kind of have access to this thing, which we've been calling B prime, I can do everything else that I need to do. Does that make sense to people? Okay, so yeah, and all we're going to do now is we're going to put these two steps together, and we get what's called the forward algorithm. And the forward algorithm works like this. Again, this should all basically be familiar before, but basically this is putting together the two steps that we had on the two previous slides. The term that lives inside the sum here is our time elapse step, and the term that lives outside the sum is our reweighting based on evidence step. And we're just going to do those two things back and forth for increasing values of t. And so you notice what we've done by the end of this is we've written down some quantity that's proportional to the evidence at time, or to my position at time t and the evidence up to time t. And I've defined that in terms of two quantities that are given to me by the BaseNet, the transition distribution and the emission distribution, and one quantity that is exactly of the same form as the one that I'm trying to compute here and is also the prior. And so, you know, basically, to convince yourself that this works, this looks like a proof by induction, right? I have my base case, which is the prior I start out with, and then I make a bunch of things that look like the base case structurally, and I define them all in terms of each other. To say this one more way, just so that people are kind of clear with what's going on, at every step, we start with our distribution over where we are now, given the evidence. We update for time, which is to say we, yeah. Do I need to do this again? Would people find it useful to talk through this slide? Raise your hands. Okay, good. I don't want to do this to death. That is actually all we have to do today. So this is a pretty short class. The one thing I wanted to show you before we leave is a little sneak peek of your next project, which looks like this. So what you're going to be doing in the next project coming up is Pac-Man is going to be trying to eat the ghosts, but doesn't get to see where any of the ghosts are, and is going to get only kind of noisy radar observations of where they're located. And so what's going on here, yeah, there, caught one, is that basically it's going to use this radar to figure out how to find the ghosts, and slowly, as time goes by, it's going to be able to catch all of them. And this is, you know, the kind of canonical HMM inference model. The true state of the world is where are the ghosts located. We never see it, but we're still going to be able to hunt down the ghosts and eat them and get all of the points, as we can see right here. So yeah, that's it. If people have questions, I can stick around and talk about kind of more general cases of this or whatever, but you're also free to go now. We win.